first speaker is actually from the Indian Space Agency. Unfortunately, they were unable to get a visa in time, but good news, they're going to do the presentation remotely. So, Subodh, would you like to take over?
Sure. So, Mr. Udupa, who is the group director of flight software that was developed for Mars orbiter mission of India, which has been a record mission from the cost perspective. So we invited him to give us a talk about, keynote talk about how they saved the cost. And without me talking much, I'll let him start now. Welcome everybody. Let me see, bring Mr. Udupa back online. Hello, Mr. Udupa, are you there?
Yeah, yes.
Okay, great. So we are starting now. This is second day of Flight Software Workshop 2014. Mr. Udupa will be presenting a keynote address on Mars orbiter mission. He's the group director of Flight Software Control group from ISRO. That's the mission that happened at a really low cost. So we wanted to know how they achieved those cost efficiencies and anything else that we can learn from them. Mr. Udupa, please go ahead. I have your slide number 1. I'll be flipping through the slides here.
Okay, good morning to all. This is Subramanya Udupa talking from ISRO, Bangalore, India. As you know, the Mars orbiter mission was a great journey starting since conceptual stage, realization, launch, orbit maneuver and Mars orbit insertion on 24 September 2014. Currently, lot of payload experiment data is collected and analysis is going on. It is my pleasure to share some of the MOM experiences with you all. My presentation briefly covers MOM objectives, scientific payloads, key mission elements, brief touching on autonomy built on board, flight software highlights, mission operations, MOM success drivers, and MOM achievements and way forward. Next slide, please.
Okay. Okay.
Basically, mission objectives are derived two major objectives. One is basically technological objectives and scientific objectives. Technological objective basically design realization of Mars orbiter spacecraft with capability to survive and perform Earth-bound maneuvers, cruise space, Mars orbit insertion, and capture the Mars and on-orbit operation on Mars. And expertise building for deep space communication, navigation, and mission planning and management. Incorporation of autonomous features to recover in case of any contingencies or failures on board. Scientific objectives are basically exploration of Mars surface features, morphology, mineralogy, and Martian atmosphere by indigenous scientific instruments. Next. This gives a basic on-orbit configuration of the spacecraft in the deployed condition of solar array as well as the reflectors. Payloads are shown in the diagram at the right side. Next. Major scientific payloads are basically 5 payloads have been flown on Mars. One is Lyman alpha photometer, then methane sensor on Mars, and Mars exposure neutral composition analyzer, Mars color camera, and thermal infrared imaging spectrometer. Next. Parent features of spacecraft are basically Mars was 1,337 kg, structure built on CFRP material, mechanism basically for solar panel driving, reflectors and solar panel deployment. Propulsion system was bipropellant, and additional safety and redundancy features have been added because long duration operation of the LAM engine, and propellant mass was 852 kg. Thermal system, basically it is a passive thermal control system adopted with heat pipes wherever required where high power dissipation takes place. And power system, basically a single solar array with around 840 watt generation at Martian phase and 36 ampere hour lithium ion battery. Adjuvant orbit control system, basically a MA31750 processor, sensors, basically star sensors and solar panel sun sensor, coarse analog sun sensors are adopted in this, and inertial reference unit and accelerometer for LAM cutoff and other related operations. Main actuators for reaction wheels, 4 reaction wheels in tetrahedral configuration, and thrusters, and 440 Newton LAM engine, which is used for orbit maneuver and Mars insertion. And TTC based and RF systems, basically telemetry telecommand systems are CCSDS compatible, baseband data handling system and solid state recorder for recording all the data on board, communication system, S-band TTC data system, and mainly 3 antennas to communicate to spacecraft in different phases of mission, that is low gain antenna, medium gain antenna, and high gain antenna. Next. This basically shows the structure where it is 1.5 meter by 1.53 meter by 1.56 cuboid structure, which is made up of CFRP material. Next. Now I will be covering major key mission elements with the basic main elements involved in the spacecraft. I'll take up the propulsion. Basically, propulsion is a liquid engine. Nearly, it should operate after 10 months. That is a long period. Normally, in our geo mission, it will be operated only for 2 or 3 days. Here, it was the main constraint, which is supposed to operate after 10 months. And improved safety and redundancy. Additional hardware have been incorporated for latch wall and other things, so that in case of non-operating, we can use that redundant latch wall. And basically, that heritage is derived from other INSAT and other satellites, where 390 liters of propellant tank was used, and liquid engine is a 440 Newton thrust it will give, and basically it is used for orbit raising and TMI and MOI operations. 8 number of attitude thrusters with of 22 Newton, and wheel desaturation purpose it is used, and for attitude control purpose these are all used. Next. Next, power system. Basically, there is a reduction in solar power because of different phase of mission. There will be a different solar radiation what it comes. Normally in Mars mission it will be nearly 1/3 of what we see in Earthbound orbit, and very low temperature and solar panel during eclipse period. These two are the major constraints. Our design was taking care to handle all these things. And solar array design maximum performance at Williams solar plus condition of around 765 watts with quite good margin. And the figure shows basically solar panel and battery subsystem. Next. These are basically showing the solar deployment test condition in the solar deployment condition. Next. Here basically there are 3 panels. One basically primary deployment takes place once. Then there are 2 panels deployed in a secondary. That means after first deployment there are 2 panels deployment takes place. This is basically test. During the test I am showing the slide. Next. Next, communication system. Basically, communication system is managing at earthbound phase, cruise phase, as well as MOI phase. The maximum range was 375 million kilometers that is required in the after 6 months of the launch. S-band deep space frequency for both CT and payload data transfer. 2 coherent transponders with 230 watts TWTA were used with 2.2 meter diameter reflector antenna. Sensitivity of reserve was minus 135 dBm. And there are sequential ranging with the 500 kilowatts ranging tone, which is majorly required for ranging, accurate ranging on the estimation of range and range rate. Integrated Doppler provision is put, and data rates are selectable, which is 5, 10, 20 and 40 kilobits per second with without turbo coding. That was the speed. Next. Basically antenna ranges are given here, basically LGA, MGA and HGA, which are basically beam widths are given in the table. And basically satellite recovery purpose, that MGA 70 meter antenna, ground antenna is used in case of, because of the large FOV, in case of loss of log condition as a redundancy. Otherwise major, all required redundancy are built on board with the autonomy logic. And high gain antenna is used with a low bandwidth, that is plus minus 2 degree FOV, which will give a full range for the satellite during the mission in the Martian orbit. Next. This basically shows the CFRP reflector deployment test. Basically reflector deployed condition is shown in the figure. Next. And this is the TMI-MC test facility where we will do the test for emission as well as the electromagnetic compatibility test with all the things, radiated condition of the full spacecraft performance is evaluated. Next. Sensors. Basically there are sensors, there are 2 types of sensors. Basically star sensor, which gives the absolute attitude in the inertial frame in all 3 axes with an accuracy of plus minus 0.05 degree on each axis. Coarse analog sensors and sonar sensors basically were given in case of star sensor failure only. Those will be used to recover from the unknown condition. And due to reduction in solar radiation, basically the core analog sensors have been trimmed to give proper sun presence signal and the attitude references in Martian orbit and all the phases of the mission. Next. Inertial system, basically there are two parts. One is accelerometer, which is used mainly for the LAM operation where orbit raising and MOA condition is used, and gyros, basically inertial sensor, which gives incremental angle in all the three axes. This basic main sensor, inertial sensor for the attitude and orbit control as such. Next. Actuators, basically reaction wheel with the angular momentum device which controls the spacecraft throughout the mission as such. Initial after the acquisition, this using the star sensor and gyros, this mode will be put and wheel will be running with 4,450 RPM with maximum torque of 0.05 Newton meter. Next. Basically AOC software if you take, these are the major modes adopted in the thing. Most of the modules are taken from earlier heritage and specific modules for FDIR, that is basically fire detection and intervention and recovery, and Mars recovery mission, basically recovery sequencer. Those things are the major modules added specially for Mars. Next. And radiation is the one basic thing we look. Basically when Mars is flown, basically nearly around 39 orbits it is moved around the Earth in the low orbit run where vallonal belt crossing it takes place, which is basically harm to the satellite, and it has crossed those things. For extra precautionary measures are taken to handle those things, and basically that all the components and shielding requirements for the current radiation levels have been put. Next. Thermal, basically spacecraft needs to cope up with wide range of thermal environment from near Earth condition with sun, Earth contribution hot case, and Mars condition where reduced solar flux and longer eclipse gives rise to cold case. That way basically hot and cold, both cases it will go through harsh environment. The average solar flux of Mars orbit around 589 watts per meter square, or about around 42% of what we experience in normal Earth orbit spacecraft. As a result of this eccentric of Mars orbit, however the solar flux of Mars varies between plus minus 19% over Martian year, which is considerably more than 3.5% variation on Earth. Albedo fraction for similar Earth being around 0.25 to 0.1. That way thermal environment is quite harsh, and thermal design was quite successfully done and evaluated. Next. This basically shows in the large space simulation chamber where thermal test was conducted. Next. This is basically thermal balance test where we will be illuminating the spacecraft to the required condition and at different phases of mission and evaluating the thermal gradients and thermal responses and comparing with the expected or predicted temperatures goes each subsystem wise, and successfully it was validated and model was quite accurate throughout the mission. Next. And I will be touching upon spacecraft autonomy built specially for Mars orbiter mission. These are the basic drives for the autonomy development. Maximum Earth to Mars round trip delay, basically that is around 42 minutes it comes during the mission. Basically it is very difficult to manage with ground as such because of this quite lot delay. Therefore autonomy was built. Autonomy is implemented through autonomous fault detection and isolation logics executed by AOC and TMTC packages, where telecommand package also contributed for autonomy purpose. Continuous watch, fault detection, isolation, reconnaissance without disturbing the Earth pointing attitude. That means basically satellite has to point towards Earth all the time so that it will be visible and telemetry will be getting all the time. Essential during communication interruptions, that is basically eclipse, whiteouts and blackout condition also, it should survive without ground intervention. Safeguarding the spacecraft during MOI, TWA duty cycling. This duty cycling basically because of the power constraint in the eclipse load support, all those things we are basically switching off the transmitters in case of the eclipse condition where power margins are less. That operation it was used. And mission requirements basically resulted in development around 22 modules in new modules, modification around 42 modules compared to the baseline software, and 19 as it is modules are used. These modules are extensively tested using simulation and flight hardware in both oils and hills test. Next. Basically autonomy, I will be covering two more slides regarding slightly more detail on the autonomy features. Basically definition, basically monitor health of AOCS system continuously and take corrective action in case of any to avoid attitude losses. Ensure power generation and communication towers are survive without ground intervention in case of any AOCS or other system failures. And objectives, spacecraft should recover from failure automatically without ground intervention by using all available resources and achieve earth pointing. That means any case of one sensor or actuator failure, you should able to survive and you should find out the resources and accordingly you should switch between the resources if it is usable and it should recover by itself. That was the basic objective. And basically on-orbit autonomy on two major components it involves, basically fail detection, isolation and reconfiguration logic and master recovery sequencer. This basically takes the input from FDR and other health conditions and it automatically recovers the spacecraft to earth pointing. Next. There are basically four levels we can categorize these autonomy features what we build. In level A, basically inside the system as such, basically health of the system is taken here, like FDA where it is a watchdown timer based system, long process detection where in case of thruster fires continuously as thruster stuck fails are detected, and EDEC for memories and memory scrubbing, MIL 1593 bus changeover logics where in case of bus failure is automatically changes over the bus as well as changes over the system. Remote programming feature in case of any anomaly or any algorithm change is required, we have a program to uplink patch so that we can modify the algorithm as such on board. Reset handling, this is one feature which is newly added here because normally in case of AOC reset condition it used to go to suspended mode where ground intervention is required to recover. Here since visibility all those things are not available, automatically reset handler there is an EEPROM content, configuration is set by those things and automatically read the EEPROM and it will come back to the configuration where it recovers to Earth. And ESCOT PROM management, this is the first time we use EEPROM on board where it needs to store certain configuration items and health conditions of the sensor and required parameter for attitude and occultation time. Also key parameters are stored in ESCOT PROM on power on or reset or loss of log condition. Those will be taken from the EEPROM and correctly configuration is set and spacecraft recovers automatically. Level B's autonomy basically for the interface related things like fault detection and isolation, it basically runs and finds out the system health and system failure detections, then automatically it will change over to healthy sensors. Next. Level C autonomy, basically it is a power safety, that means in case of power emergency case or let us say power drain is there, automatically power battery bus as well as currents are detected and automatically load shedding operation takes place and it goes to a minimum power condition configuration, then it will look what are the faults and it will recover by itself. AOCS safe mode where earth lock is lost, there is a watchdown timer which basically indicates that there is no communication between earth and satellite and it reverses by itself. And master recovery sequencer to handle more than one failure, that case in case of star sensor failure or in case of gyro failures, automatically it goes to the other thing and two failure cases it will recover through other sensors which is available, the sensor and actuator. And level D autonomy basically for operational autonomy where operations like launch sequencer where deployment sequence, other sequence takes place automatically. LEB sequencer that is for LAM operation and orbit raising. Thruster augmentation logic where in case of thruster struck failure automatically it selects the other set of thrusters and it will isolate the thruster which is stuck in high or low condition. LEB termination criteria where when delta V is achieved automatically accelerometer cutoff is taking place and do the operation. And payload operation sequencer which is used during after reaching the after reaching the Mars orbiter where payload operation takes place like maneuver, imaging and coming back to earth pointing, all those automatically takes place. And other logic, supporting logic such as SS occultation depends upon the predicted time. It will automatically senses it is occultation region and once occultation region is over it comes back to takes the update from starter and controls the attitude. Overspeed logics for protection logic for wheel speed, basically it is like cutting off the torque to the wheel and selecting the redundant wheel in case of failure. And reference check logic, this is one logic where in case of loss of log attitude, loss of log conditions where it will know the pre-defined reference which is periodically updated to EEPROM. In case of loss of log, it recovers to using the star sensor data, it recovers to the reference condition which is put as earth pointing. Next. And this shows a context diagram of master recovery sequencer. Basically here approach used is normally all earlier baseline software was used for other satellites are reused here and without touching those software, additional software required for FDIRs and master recovery sequencer are built and interface so that main software will not change and only modified software is thoroughly checked and interfaces related to those are thoroughly checked and all the test cases generated for as complete. Here you can just see master security has interface with AOC's logic and FDR, similarly EEPROM data and TCP, which is basically a command processing unit which does basically event generation, and it will automatically like switch on, switch off sensors, or in case of event or programmed event has to execute, set of command to be executed, all those things are taken place through basically this smart security sequencer. Next. This basically shows the spacecraft autonomy realization. You can just see all the subsystems involved in the basic autonomy or communication system, where basically it is used to communicate to the ground, where there are TWA, which are high power dissipating elements, which depends upon the power condition. Judicially they will be switched on and off, depend upon the condition. And power, where the lithium-ion battery charge and discharge cycle control, or similarly emergency condition recover, and basic parameters related to telemetry parameter related to battery, solar array, all those things will be used for the logic. Actuators, reaction wheel, thruster, and basically there is a solar array drive mechanism which basically points towards sun depend upon the command. Here particularly in case of loss of lock, automatically search sun and then it locks to sun. Sensors, basically there are 3 gyros, that is the inertial units, 2 star sensors and 4 accelerometers, that is textile compressors they have put. Accelerometer is used basically for the cutoff type of thing, where delta V, when it is achieved, automatically it cut off. Remaining 2 sensors used for attitude control. And basic processor system, if you take telecommand system, which is in the left side of the slide. Similarly, AOC system, that is right side, where basically health performance analysis it does, fault detection it does, isolation reconfiguration through events, and basically internal reconfiguration also it does, battery voltage and current monitoring check also it does, safe mode detection and normalization through event. Basically here all the detection takes place and real command execution takes through TCP, which generates the command for other subsystems. That way basically all are communicating through MIL1553 interface, and basically telemetry parameters, whatever is coming satellite from the battery and other things comes from TCP to AOC. That way the diagram shows most of the places TMTC interface with TCP, and actuator and sensors are interfaced through AOC, and AOC and TCP communicates through MIL1553 interface and for certain command interfaces. That way overall, if you see, these are the basic elements of autonomy realization. Basic software resides some in TCP as well as certain software resides in AOC processor. Next. Flight software, major highlights I will be covering here. Basically it is developed in ADAS with MIL-STAT 1750 processor, sensor processing and actual control, basic elements of the software, autonomic features, on-orbit models, helicentric and Martian phases, onboard attitude steering and mission profiles including LEVs. These are basically model driven as well as coefficient based things have been put. Ground software, basically orbit determination system considering range, Doppler and letter DOR measurements for various phase of missions, precise measurement and modeling, and orbit computation using accelerometer data for earthbound and Mars orbiter insertion operations. Next. This is basically giving a brief of software development process. It is common to follow to most of the satellites, except here thorough test in the system level as well as in the integration condition level, and oils with the real system connected in condition, so that end-to-end analysis and all the test cases have been given, and additionally any sequence has to be executed on board. Basically those things will be simulated on ground and real results are verified, expected versus observed. Then only it used to be uplink to onboard. This is an additional work is carried out for, especially for this Mars mission. Here you can see all the requirement generated like 1, 2, 3, 4, those things. It will go through a requirement review, then it will go to module design and design review, then modules will be developed for coding, then code will go to internal unit level testing as such, then all the things will be integrated and integrated level testing takes place, then basically hardware and software level integrated level test will take place, and independent QA validation for testing and verification. That way, this is the total flow of the development process adopted for this. More or less, it remains same for most of the satellites what we developed. Especially here, we have taken additional care to see that all systems are integrated and additional tests were carried out. Next. This shows basically a spacecraft in launch configuration, total satellite in the launch configuration. Next slide. This is basically launch pad integrating with the vehicle. And next. Basically launch vehicle, this is basically a normal PSLV vehicle which is used for launching normally I-1K satellite, where is that 1000 kg to 2000 kg satellite, normally 1100 kg is the capacity. Here basically because of the augment of perigee which needs around 245 degrees, it is basically certain modifications have been done in the software to achieve this. And 3.5 meter diameter and 40 meter tall, this lift off mass is around 320 tons. The first and third stage using solid motors, second stage employs turbo pump fed bipropellant Vikas engine, fourth stage employs pressure fed high performance bipropellant liquid engines. Long coasting of vehicle carried out before separation of satellite to get the required augment of perigee, one of the critical orbit elements for Mars orbit. Basically to achieve the inclination on Mars arrival, basically this was this specially done for this vehicle. That is what extended operation of the PSLV vehicle. Next. Launch took place on November 5, 2013. That is basically by PSLV XL. That is PSLV C25 mission. The launch day was selected for its minimum energy transfer opportunity for Mars. It occurs once in 26 months. Because the target schedules, all those things are fixed. Based on those things to achieve in 2014, September 24th was the real Mars insertion, what we want to do. Based on that only all schedules are worked out. We are worked for that. And launch put MOM in 248 in 23,500 kilometers elliptical orbit. This is a perfect launch. Next. I will be covering now basically mission profile to reach Mars, what are the things done. Basically 6 liquid engine burns took place basically for gradually to increase the to reach the Mars, where hyperbolic trajectory of spacecraft to escape from Mars to come out of Earth's sphere of influence with Earth orbital velocity with delta V boost. Spacecraft leaves Earth in a direction tangent to Earth orbit around Sun, encounters Mars tangent to its orbit around Sun. The flight path is roughly one-half an eclipse around Sun. The spacecraft arrives at Mars SOE in a hyperbolic trajectory. When the spacecraft reaches Mars periaxis, it is captured into the planned orbit around Mars by imparting delta V retro. Basic delta V total required was 2.5 km per second, where it is basically apportioned. Delta V boost was around 1.5 km per second. Delta V retro was around 1 km per second. Next. This basically gives the details of earthbound manuals what you have done. Basically LAM burn from launch, you can see EBN 1 to EBN 5. One 4A was there intermediate, where there was certain performance degradation was there in a particular operational condition. Then that was corrected by using event 4A. And similarly Mars Transmars insertion. These are the things actually dates what we conducted, and basically achieved is put in the last column of the table. Basically it was spread around 19 orbits, and total earthbound orbits are being managed by delta V cut off by the accelerometer, and basically planning all those things are judicially done. Next. Basically TMI operation. Basically here there are 3 phases. That is basically MOM spacecraft was put into way of Mars by performing TMI on 4th December. Then heliocentric phase. After TMI, the spacecraft entered into an elliptical helicentric orbit that is designed to intersect Mars orbit around Sun. Then trajectory correction maneuvers, where basically TCMs, these are all for correction of the orbit to reach Mars. That is subjected to 2 TCMs to correct the effect of small forces, angular momentum dumping, and errors in navigation solution propagated during the heliocentric phase on 11th December and 11th June by imparting a total delta V of around 9.33 meter per second. This to basically correction maneuver done to reach Mars. Next. This just shows the ground segment, what mission control room of our thing. Next. And this next 2 slides basically covers the MOA operation, how it was planned. Basically before T-10 days, all the uplink required for MOM operation were uplink to the satellite, and basically timeline, everything was set. You can just see in the diagram all the operations what is carried out T-10 day, T-9, T-3 and T-2 and T-1 day. Like that the operations were timeline and sequenced in a uplinked programmed condition. All are executed to time tag commanding, where automatically it executes the total operation in sequence. Next. This also shows the basic events what are taken place during the maneuver, then basically firing of lamp, then again reverse maneuver to point towards earth and support of antennas, data rates, and different events are listed in the timed bound manner. And basically here you can see the TWTA operations depends upon the eclipse entry and other things. Those are all operated in on-off condition so that to save the power, because that MOA took place in the eclipse conditions where eclipse coming out of condition. Basically we want to save the power. Those are also planned through automatic sequencing on board. Next. Now I come to basically MOM success story, how it happened. We contribute the success to quick and firm decisions. That means basically what it is done here to achieve in a predefined target, spacecraft configuration finalization. Basically all the elements which were used, supposed to be used for Chandrayaan-2 have been diverted here. Had been development time got reduced because most of the hardware like AOC, TMTC, power, inertial system hardware were available, which was basically put into use in Mars, and hardware diversion versus procurement versus new. That means we judicially took a stand which are the elements which can be diverted have been diverted to Mars, and the new development all those things we minimized, and procurement all those operations also were limited so that all the resources available are used here. And mid-core correction you can see basically certain decisions are taken like solar panels. They are actually basically they are thinking of fixed solar panel, but finally if you see the angle required for motion throughout from Mars launch to Mars arrival, basically that angle was very minimum, that is within some 40 plus minus 40 degree motion only was required for solar panel. Therefore a simple rotational mechanism where offsetting can be done to achieve the power generation was decided with a simple stepper motor sort of thing is put, so that basically this type of depend upon the phase you can command the spacecraft automatically to take the data from EEPROM and use it for the pointing of the solar panel correction required throughout the phase. Then S-band system, there are two things, S-band or X-band system development was thought, and it was X-band was dropped and S-band only was used here so that it is minimizes the time for realization. Similarly, there are cross coupling of receiver to telecommand system was there, which was simplified, and delta device package inclusion. This was required for accurate measurement of the range and range data, and plane also was like the trajectory plane also was determined will be using this. This was introduced, and reviews. Basically, standing review committee for autonomy requirements. Basically, this is a new things developed for Mars. Therefore, thorough review and test case reviews, test result review, all those things took place very judicially and in a strict manner. That means a separate committee is put to look after all these things so that there is no leverage between the things. As and when it is ready, that was reviewed and cleared. That way it was possible to achieve in a faster duration of time. Next. And you can see there is no compromise in test and development process. That means all the processes were followed for the software development or hardware realization, testing, verification, all those things are followed judicially, and there was no compromise on test. All the cases were tested as well in the system level, as well in the integration level and ground checkout level, and all the things were simulated using the system available in the simulation environment and verified. And there is an independent V&V team which parallelly takes our software and hardware, and they will verify independently, they will carry out the test cases, result tabulation, all those things was done parallel team. That also one confidence it gave for us to see that everything there is error free. And budget, schedule and logistic management, there is a best support we have got from the project, both in pre and post launch operations. Then there is a standing review authorization board, that is spacecraft authorization board, which reviews the mission operation, simulation results and guide the mission team to carry out flawless operations. That means each operation, before operation, they have been reviewed, they have been tested in the ground setup, and then only they are uplinked to the onboard and seen that there is no operation related error or contingency arises from this. That way it has given a good support for us to see that flawless operation. Similarly, management support. Anyhow, it is required for any mission. but really they have supported quite a lot, and whenever required it was supported. There was no any lag in any of the decision making as such. Next. This we contribute the success to teamwork. Basically, you can see launch vehicle, satellite mainframe, payload, integration and test team, ground checkout team, mission planning and operation team, science team. All these teams are worked hand to hand and see that all the delays what can occur in the discussion or reviews, all those things are sorted out as and when it came, and we minimize the time during the thing and focus the meeting so that all the decisions are arrived at first meeting itself. That way, real teamwork only we are able to achieve this mission. Next. Reduction cost, I will talk certain things. Basically, ISRO design, develop, test and integrate. That means basically ISRO only does all the required thing. It doesn't involve third party for manufacturing. Industry law is limited. That means basically for testing and other things only, we will utilize industry support. That way, basic cost we have reduced using that. Manpower power cost is also less compared to other countries. Procurement cycle and project cycle are de-linked. That means especially for project there is no certain thing. All are procurement as a part of the procurement cycle it came, and it is used in this project particularly. That is the reason also that long duration of procurement, all those things are not there. Project execution time less. That is test as you develop. That means basically as and when it is tested, developed, it is tested. That way parallel teams are working on the thing. That way you are able to reduce the thing. And utilization are pre-used modules. That means for software development, if you take, most of the modules are reused as such. That way development is required only specially for MOM requirement, whatever they are only were developed. That way cost was very less compared to other missions. Next. Just I will be touching on certain anxious moments, that is delivery of subsystem at flight deck on time. That is basically to meet the schedule. Otherwise, we missed the bus in 2014, it will go to 2016 or 2018. This is the minimum energy we can use to achieve the Mars orbit as such. At spacecraft level, thermal balances. Basically, thermal, it was totally a unknown thing for us because it has to support in 3 different phases: thermal loads and other things, analysis, and that estimation what they are done, verification. Really, it was a tough thing which we have done as a challenge, and it was completed. And precision launch by PSLE. This is also one of the important thing we are looking at, achieving basically that to achieve that whatever fuel we have loaded, optimize use of that fuel to have that PSLE has to give a correct orbit and the correct that attitude of perigee what we are expecting. That is perfectly it gave the thing. LEB operation, that is basically for orbit raising and fuel conversion. Each and every LAM operations, LEB operations were planned, and basically they are estimated the performance, what will happen and how much fuel you will save, and judicially errors, all those things are estimated, trajectory required or attitude orientation. Those are all perfectly done and validated so that nowhere we lost any additional fuel. Transmass injection, that is one of the important operations where we judicially carried out the required conditions, tested all the things. That way we were able to achieve the thing. Performance SLAM after long duration. This is also one of the things, because all other missions we basically operate the liquid engine within 3 to 4 days of the mission, but here almost 10 months it has to operate, and really it has operated well, and we are able to achieve what we want. And getting into Mars orbit, it is basically a blind operation where during that Mars orbit insertion, satellite was not visible during the insertion. Only after that came out only, after receiving telemetry only, we came to know that it has captured Mars. Really it was a moment which we felt very excited. And first image of Mars, that means after reaching the Mars we took the photo, then only we confirmed it is properly done all the things. Really these are the incidents which really was anxious for us. Next. This 1 or 2 snaps I will be showing image of Mars. Next. Next. This is Mars viewed by MOM. Next. Next. Okay, slide number 50. This is full disk of Mars taken through that Mars color camera. Different color things are taken like green, red and blue. Then those are all combined to get the color image of the Mars. That way this is one photo we took 3 and then it was combined to get a better color view of the Mars. Next. This is basically that satellites of Mars, that is the demos, one viewed by MOM. Similarly, next slide. This is Phobos. Basically, you can see the black dot there because this is an animation was there, but here currently, since it is PDF form, I am not able to show that. Otherwise, it is Phobos photo taken by mom. Next. Now, Saturn, basically whatever achievements what we tell by Mars, I will be listing out. This is basically a unique launch, vehicle trajectory and mission concepts. Basically, it is specially designed for vehicle trajectory and Mars orbit and estimating of the basic range and range rate. All those things are for deep space mission. Those are all required, but those are the concepts we have proved here. And first interplanetary mission by India, this is the first time we are going. First Indian spacecraft to escape the SOI, that is Earth and orbit of Sun. And first Martian to world to succeed in TMI in first attempt itself. And first time two spacecraft from different agencies, like ISRO and NASA, it was reaching more or less in the same time Mars orbit, almost simultaneously. And most economic interplanetary mission in the world, realized with a budget of around 450 crores Indian rupees, around $75 million, including launch, vehicle, spacecraft and ground segment development, all total costs together. Next. This is shortest project schedule realized. That means around 15 months we took to from conceptualization to launch. That way space, launch and ground segment, all development took place within 15 months. Youngest team accomplished. Most of the people who involved in this Mars work, you can see more of the people are young people and they have achieved this in short time. First Indian spacecraft to successfully survive Van Allen belt, really crossing 39 times. Basically in Chandrayaan 1 around it was 12 or 13 times. Here it was 39 times it was crossed that belt. First Indian spacecraft to incorporate full-scale onboard autonomy. This is one thing which we built and now currently we are using for all other satellites also this concept. This is the first time, it was an EDS and we developed, tested and really it has worked successfully. And first to Mars with spacecraft not encountering loss of log. That means there is no loss of log or any contingency condition occurred throughout the mission. Then first to use shipborne terminal, that is the initial tracking when it was launched. Shipborne terminals are used to track the satellite, this is first time in ISRO. And project go online, that means basically all the operations which are taking place are online available and there are Twitters and Facebook, it was getting updated. This is also first time it was done for other satellites. We are not doing that earlier. Next. This is my, that basically what we got from the Mars mission, if I take for way forward, like you can see the pre-mom and post-mom if I compare. Basically project specific systems, like the maximum number of systems were basically specific to particular project. But now currently standardized system, that means standard systems will be available. We can plug in those systems for any of the spacecraft. That means spacecraft can be manufactured or realized using those systems. In-house systems more, vendor systems. Basically here till now we have in-house systems developed. Now we are going for vendor system development. That means development, testing, although through a separate agency, those so that we can dictate the schedule. Project-based procurement. That means procurement is taking place based on projects. Now it has become programmatic. That means the program will be procuring so that project procurement will be, but it is a subset of that. And other drawings and other things like project specific it was becoming, now it becomes standard because like you select the particular type of bus, it becomes standard. Made to order, that is project specific bus systems. Now here become off the shelf bus systems where we have system available and I can use it for satellite. Then made to order, that is basically spacecrafts are made to order, now it become off the shelf. Meeting, quite lot meetings used to take place for the spacecraft realization. That is now we have minimized it. It is in MOM, especially we experimented this and we are able to achieve it. Individual databases, that means project and different depend upon the phases. There are so many databases are there for command, telemetry and other related mission operation databases. Now those are all been arrived at a common database for bus and different phases as well as the mainframe systems. Testbed, basically we used to have oils and hills, that is online simulation thing and hardware in line simulation. Here now concept has come. In addition to oil and hills, we have subsystem interconnected condition. Test beds will be made so that any operation can be really validated on ground before uplink to the satellite. That concept has come. And project driving the R&D, now it becomes production derives the basic project drives the project and technology development drives the R&D. That is the normal what we see change from MOM to post-MOM. Next. This I come to final slide of my presentation, where I want to acknowledge all the mom team who contributed in preparing this material and helping us. Sincere thanks to Mr. Arunan, his PD Mars Orbiter Mission, project team supporting for the preparation, and Dr. Annadure, who was PRD, who gave valuable guidance throughout this preparation. I thank Sri Vasanta, Deputy Director, CDA, for his valuable guidance and suggestion in preparing this material. I thank Dr. Shivkumar and SK Director Isaac, Dr. Radhakrishnan, Chairman ISRO, for providing opportunity to present in this workshop. I thank Dr. Alan D. Yunal, Chairman SSW 2014, and Dr. Harmalkar Subodh for innovating and giving the great opportunity to participate in this workshop. I thank all the distinguished delegates and domain experts who made me feel great by presenting about Mars. Thank you.
Thank you. So we should open up at this point to questions and answers.
Yeah.
Dr. Unel is going to get the microphone to anybody who has questions. Amale has the first question.
Yes.
Yeah.
My question is a software question. I wanted to know how the use of ADA helped in reducing software defects. And I also wanted to know ISRO's history of using the ADA programming language. And also why were languages like C or C++ not used?
How it helped in software development, and why any other languages, and C why it is not used. It is used, you can tell.
Okay. Now basically, it's ADA language. Basically, it is a strongly typed, and we are using that form. It has a quite good heritage in our software development. And basically, what we see is all the types of error, programming errors. It automatically gets caught during initial compilation itself. And basic support structure, all those things, what is provided in ADA, it is quite user friendly, and we are well fluent with that. That we are quite long since we are using this language, and we are developed that, used that language for developing here.
C we are using for subsystem like C.
Yeah, C all language will be using for subsystem certain, like small subsystem where, like in test system and other places, where it is like application dependencies basically for a smaller application like payload and other places, not like major control system where attitude and orbit control, which is very critical system in the spacecraft, we use the ADA language.
Okay. Thank you very much. Next question.
Okay.
Thanks. I'm very impressed with the work that you did on MOM, and much congratulations there. I had a couple of questions regarding the magnitude of the project. One question I had was there's like 82 flight software modules. Do you have an estimate of the number of lines of code in those 82 modules?
Can you just repeat the question?
Yeah, so they are in, he's interested, he's estimating that there are about 82 software modules in your, for this mission, and we would like to know what's the number of lines of code in that?
Okay, total number of lines, it is around 60,000 lines. Like ADA lines if I take, it becomes around 65,000, and basic like PROM if I take final, it will come around 190 or 200K. Kilohertz.
So that is 200,000 lines of including just the flight software or flight and ground?
Flight software.
Okay.
Yeah.
Can you please repeat it one more time? It's about 60,000 you said, or?
Yeah, around 60,000 lines. ADA line, basically if I take ADA code, Then basically, if you convert that to final fuse prom, if I take, it comes around 200K.
Oh,
12
in the
kilowatts.
prom. I see. So 60,000, so let me repeat it. So the
Yes.
way I understand it is 60,000 lines of ADA code,
ADA code. Yes.
when it gets compiled,
Yes.
it goes to about 200 kilobytes or something in your
Kilowords,
prom.
kilowords of prom.
Kilowords of prom. Okay. And one word is 2 bytes or 4 bytes?
Yeah, 2 bytes. That is basically
bytes.
16 bit.
Okay.
And one other related question. I was curious how many people were on the flight software team, the V&V team, the QA team, and the standing review board team?
So let me repeat the teams he's interested in. He's
Yeah.
interested in knowing how many people were in the flight software team, test team, V&V
Yeah,
team.
basically around 8 people are there in the software development team
And equal number.
and equal number in the quality assurance, software quality assurance.
I see. And how about your review team?
Our review team is basically a standing review team. It consists of different domain experts in software and system level people. It is almost 6 to 7 people will be there in the team. And basically we review the requirement, that is like software specification review. Then it will go to design, like preliminary design and detailed design review. Then after code development, basically code review and code inspection. Then basically unit level testing, integrated level, that way it goes. And overall test result in the integrated whatever done, again it will be reviewed by a separate team and validates it.
And also the QA team? I was wondering.
The QA team was how big? Quality
Around
assurance.
8. That's same. More or less
Eight, okay.
design team and QA team is more or less same.
Same.
Because
Okay.
here quite lot validation was required and each and everything was thoroughly checked independently. That is independent V&V. Therefore, more number of people were involved in this.
I see. Okay.
All right, thank you very much.
Thank you.
Thank you.
Can you give an order of magnitude for how many scenario level tests were run to qualify the software? So tests where you actually set up the simulator and the software to run a mission mode and did an activity or injected a failure. So about an order of magnitude of how many tests. Were any tests run after launch to make sure that the system was going to be successful from a software standpoint?
All mission scenarios are done.
Okay, basically total all the mission scenarios were
Test cases are
Yeah.
10,
around, we approximate value I'll tell you, around it was 10,000 test cases we can tell. And basic fundamental behind that was all the scenarios which gets executed in mission as such, all those conditions were tested in an integrated condition by simulating the scenarios and recording the results. That way each and every function scenarios have been given and verified. Then auto tests that like boundary checks, that type of normal tests will carry out as such. Here specially scenarios have been given for each functionality, each phase of mission, what are things take place. For example, sequencers, that type of where complicated timing things are involved, different options take place. Those all the scenarios, each and every scenario, like fault condition occurs, what happens, then for FDRs, then recovery sequencers, and operational sequencer, all those things are scenarios have been put and checked. Approximately around 10,000 test cases we can lay.
Post-launch also we have done mission
Yeah.
scenarios.
And post-launch operation also, quite a lot simulation have been done before operating really on the spacecraft in a simulation environment. Those are additional, like that specific to that scenario, like that values, like database, that's specific for that condition. Like earlier we had like a set, here basically with that specific value it has to be tested before real operation on board, like uplinking orbit coefficients and particular sequence working. All those things are special tests during on the mission, like before operating really on the mission, they have been given and tested.
And have you observed any spacecraft behavior or response to the environment the spacecraft is in that's different than what your simulators or analysis predicted?
Difference.
We didn't find any
Basically we have not find any major as such, but certain places,
but solar
yeah.
generation was higher.
yeah, like basically we take solar panel generation estimated versus real observed. There are quite slight difference. Like it was higher basically. Our estimation versus predicted versus what we observed, it was slightly higher. See that way, certain thing margin more was there. We estimated really slightly less compared to other things. That way, certain mismatch of that sort are there. And scenario testing, certain cases where we have seen certain the small like database setting related, certain scenarios when you check certain problems we have seen which we have corrected as such. Otherwise, basically like one example I'll take. Basically, we thought in case to take care of redundancy, like that LAM engine, it has two coils to operate. Like one failure is there, automatically with one coil itself it can operate, because MOI condition where we thought that redundancy, like in case of coils were to be lost, to avoid that we thought both we can energize and do the test. When we done a test, we found that both coil energization was causing not to operate. See that way certain inputs of that sort, which even though in a system level it was realized, but in the final system when it is integrated condition, we found certain that type of setbacks, which finally we decided to augment instead of LAM 2 coils, thruster augmentation sort of thing. And like that certain one or two observations we have seen. Otherwise major there was no errors as such.
Environment-wise, no. Nothing.
Yeah, environment-wise there is no effect on the spacecraft. It was really good. No upsets we have seen, because we have a monitor for SU and the data recording is available on board, memory upsets. We have not seen any of those things.
Okay, thanks. Thank you.
Hi, congratulations on your great success. My name is Kalyani Rangarajan. I'm from Aerospace.
Thank you.
I want to know, you mentioned that all your development, design, testing, etc. were also all done by ISRO. Were the hardware and the software team co-located? How often did you do the hardware-software integration? Thank you.
Done within ISRO, how often hardware and software team interact? Is it that?
No, can you just repeat the question?
Yeah, so she wanted to know whether the hardware and software team was in the same building or were they co-located? Location was same.
They are working together as such. There is hardware and software team will be closely interacting. It is like in the same building and same group. For example, if you take attitude and orbit control system, there is a team for development of hardware. Similarly, there is a separate team for software, but it is in a part of a single group. That way, like test system, all those things support also is part of same group. That way, it is basically like a cohesive thing. Due to that only that independent IV and V we give, so that because we want an independent evaluation. Evaluation team is separate, it is in a different building. Basically, we supply all the information, test results, what it done, design level, all those things. Independently, they will validate. They have a system to evaluate our software as well as hardware. Timing, all those things they will analyze and put. But software, hardware, design team, all those things in a under same group, basically.
Okay, so there were more integration between hardware and software were more frequent than it would have been if you had an external hardware contract or something, right? How often did you do the integration?
Closely the more integration. Basically, it is like when you develop, all the issues get sorted out when they discuss and do it. See, instead of hardware development independently going, software going independently, and basically depend upon document alone. Not a lot of issues we have seen earlier. Here it become very close, and each and everything was discussed. That way it went through.
Was there what was the software development methodology you used? Did you use any modeling, or can you talk more about your software methodology?
Yeah, basically what we use is a object-based design, and it is approach is basically in the architecture it is a top-down, and when development stage it is bottom-up. Basically, we define all the elements of software and like basically different layers like interface layer, application layer, and remaining interfaces related to application layer. Like that, basically layered architecture is there. and round-robin type of scheduler, which it executes task periodic thing in a time interval manner, time synchronized system, and we are not using interrupt except for this like watchdog timer type of thing. Okay, basically we have a process control that is basically derived from IEEE 12207. We have a ISPD document which basically tailored version of IEEE 12207. We applied strictly that development process, that part, completely, as said. That means all go with the process line, like modified water model what we follow, and requirement, finalization, then design, then coding, testing, that way, everything as per the process.
So, can you, Amal, would like to know what was the IEEE document that you referred to?
That is IEEE 12207.
12207.
207, yeah.
Other questions?
I think it is 9:30.
That's okay. I actually, no, I have a question.
Oh.
How did you, again, congratulations. How did you separate the purchasing cycle for hardware from the project life cycle?
Okay, because we have used the existing program element because we have coming from the other program element is there. We have diverted, as Mr. Udupa has told, that the Chandrayaan project.
Yeah, basic, if you see, actually, major, if I take the elements involved for Mars, if I take for spacecraft elements, like attitude orbit control system, command or telemetry package, or the data handling package, these are all basically developed and available modules. Like, for example, current satellite is a particular satellite, it is developed. Here basically for Chandrayaan 2, those were developed as such, and those are all reused directly here. Basically, those are all even directly fittable here. That means more generalization was there. There is no procurement time is involved. That way it is readily available thing. See, that way relation schedule was able to crunch.
Procurement was not.
And procurement was not involved in such cases, except for one or two where procurement was there, like TWTA, one or two elements of that sort is there. But those are which can be integrated at the end of spacecraft integration. See, that way that doesn't need any major thing. All the tests can be completed, satellite can be closed, then it can be mounted because it is mounted nearly outside condition. That way one or two elements of that were dictating the schedule. Otherwise, remaining all were, most of the things were available, and certain things were, since it is standard, it was developed fast. That way we were able to achieve the things.
Well, again, congratulations. What an amazing success.
Thank you.
Yeah, thank you very much. We realize it is 11 o'clock in the night at your time. We really appreciate you staying awake and telling us about all this. Thank you very much.
Okay, thank you very much.
Okay,
All
do we
right.
have a break?